I think there's something that's somebody's trying to figure out a way to make my life more difficult. All right, so here we are, example 17.1, and I'm going to go step by step through there. And maybe I'm going to grab my book too and flip through the pages so that you can flip through the pages. And there she is right there on the ground. And so we're going to go to chapter 17, and I will try to show you. I am your tour guide to the book, Shigley. That's my Monty Python in French, by the way. Go away. Oh, sometimes do the second time. That was terrible. I could do much better than that. All right, but that's not why I'm here today. So we have this belt 6 inches wide and transmitting 15 horsepower with light shock conditions. So they give us a service factor of 1.25. Factor of safety 1.1 is appropriate. Pulley rotation parallel, 8 feet apart. I think we talked about this already. 6-inch driving pulley, which is kind of weird because it's a 6-inch wide belt. So that means it's kind of like a square looking thing. You would think the belt would be narrower, but anyway. 1750 RPM and 18-inch diameter driven pulley. And the factor of safety is for unquantifiable exigencies. And you need to see me bigger, right? So you could see the expression on my face as I go, huh? Okay. And I wonder if this thing makes it too small. No problem. Who cares? We want to estimate the centrifugal tension here and the torque, and estimate the allowable F1, F2, Fi, that's the initial tension, and the allowable power, and then estimate the factor of safety and decide whether it's satisfactory. Okay, so here away we go. Something we might want to do is do the geometry first. And from the geometry right here, we can see, I think we want to use, I think it's this little diagram right here. Is this diagram? Yeah. So I'm not sure if there is, yeah, there is. Here's one right here. There it is, shows right there. See that equation right there? That's going to get us that angle. And we're only going to do it for the small pulley. I think that's all we need. I don't think we need to get this other one. But you can see that that one had slightly different right here. So we're going to do it in radians, by the way. But it'd be a good thing to check on what the angle is going to be. It's kind of be interesting, I think. So that's how we're going to make the thing. It's also going to look like a theta right here, but it's going to be pi minus 2 sine of the inverse sine, big diameter. So this guy's going to be big D. He's little d, minus little d, divided by 2, and the center distance, which I can't quite figure out. I don't know how they figured that out right there. One of these days I'm gonna pick it apart. One of these days. I have done it before for things, but it's like that's a little obsessive. So 2 times the inverse sine of 18 minus 6. Is that right? Let's make that of the whole thing, right? Made that disappear. And divided by 2 and 96. And we get 3.017 radians. And if I do a little calculation, I get 172.8 degrees. I'll buy that. Okay, so it's really just 180 degrees minus a very small angle. That's because they're very far apart, right? It's nearly tangent to the thing. And we look up from table 17.2 the material properties of this thing, and we could find, if we did, we would find this thing is, what did they say the thing? It was polyimide A3. So it has a thickness of 0.13. It has a minimum pulley diameter, so we're totally fine. It has an allowable tension per unit width, right? So that's going to be, I think we just call that FA, right? So when we see FA, that's what they mean by it. And we'll see that it's based on 600 feet per minute right there. We also see that it has a specific weight of 0.042. They actually gave that as part of the problem, and a coefficient of friction of 0.8. So we needed all of those things from that based on this material right there, right? But they did give it to us down, that one part down there. So from table 17.2. For that poly stuff, we already got that weight density, okay, but I'll put it down anyway. Pounds per cubic inch, and we found out our belt thickness, 0.13 inches, and we found out our coefficient of friction, which is pretty important right there. By the way, coefficient of friction is not something it's not a very reliable thing, right? Because it really kind of depends on the condition of both surfaces, right? When it gets a little rusty, get a little dusty, get a little greasy, get a little wet, get a little, well, I don't know, whatever. Somebody put like pine tar inside there, it'll get better. I don't know. Something. FA was 100 pounds per inch. And remember, that was the allowable tension per width right there. Allowable tension per width. So, given that, we do step 1. And step 1 is to find this guy right there. So he is, I don't know why we had to define, actually, I don't even know where we ever use it. That's okay. 3.017 times 0.8. All right, so now we have that. That's 11.17. Woo-wee, now we know. All right, the next thing we want to do is find what the velocity is going to be. Right, so we'll find the velocity of the, this is like the nominal velocity, probably at the belt right here, just like maybe at the end right there. It's going to be the RPM times the diameter divided by 60. So just like in gears, all right? So we're using the same thing. We're going to get feet per minute. So we get pi 1756 divided by 60, and that equals 2,749 feet per minute. I'm getting sloppy because I'm tired. I was up late last night. It's 9:40 now. Don't know where I'm going to get any more sleep, but okay. Now we need weight per foot. All right, so that's in the calculation for the FC. We end up, it's kind of weird that we turned it to feet per minute, by the way. And I just wrote nim, didn't I? Okay, so we need weight per foot. And we're going to see in a second that it was weird that we divided by 60, because we're going to divide by 60 again, I guess, and make it per second. That's weird. We multiplied. I don't know what I'm doing. Yeah, no. Okay, we did by 12. There you go. I don't know what to tell you. Okay. I'm going to write little w. Little w is weight per foot, and that is going to be 12. And we're going to take that weight density, and we're going to take our width, and we'll take our thickness, right? So, yeah. This is pounds per cubic inch, right? And then multiplied by 12. So that's going to give us the weight density of the thing. And so not the weight density, but the weight per foot of the thing. And so we go that it's going to be 6 inches wide, 0.13 thick, and we get 0.3931 pounds per foot. I did write all this out, by the way. Wrote this out really nice and long. See how nice and long it is right here. So I carefully went through this example. 2. So now we're able to get with, what equation is this? Let's double check what equations we're using so I can call them out. I can't find it. Where'd you go? Where'd you go? Oh, there you are. It's called equation E right here. So if we wanted to find it, this is equation E right here we're about to use, right? So we're going to use, I'm going to use 32.2 because 32.17? No, I'm an engineer. I'm 32.2, man. What the heck? Shigley. What do people do that for? Let's just all use the same thing. People over in the physics department, they just go like 32. They go 9.8. What happened to 9.81? People. Anyway, we're going to use that. I guess maybe they just think I'm the bad one. I'm the wrong one, but I think they're wrong. Okay, so we're going to get this. And we're doing it per foot. Yeah, I guess that's going to work out. I hate it when I don't know the units. I don't like not knowing the units of this thing right here, right? So, what happened here? Oh, I guess it's because it's trying to save energy because the battery. Oop, and there you go. He's turning off too. We got all kinds of things going on. This is going to be such a great video. We probably won't make this again. Yeah, no, I'm going to turn it off. Okay, good. Well, I don't have to worry about it then. All right. So, anyway, units. Yes. This is pounds per foot. So we're going to divide the thing out there. And then it's going to be slugs per foot. And this is going to be feet per minute squared. What happened to the units in this thing? I don't like it. Man, I don't like the units. All right, so we get like gotta write the thing out. I should pause this video. No, I want to know. If I get slug per foot right here, and I have feet per second squared, it's just not going to work out right here. It's going to be like pounds per foot is going to be what I get. And the other thing, are they all on a per foot basis? Is that what the whole thing is going to be? I don't think it can be. No. It just bothers me. Well, I guess actually on one level, okay, so what we could say here is that we have, slug feet squared per second squared divided by feet right there, right? Oh, that makes sense. Okay, yeah. So, yeah, slug foot per second squared is a pound. I'm satisfied. Otherwise, it would be like kinetic energy. It wouldn't have mv squared, wouldn't it? But and energy would be foot pounds. But now it's per foot, so it's pounds. I'm satisfied. Enough-ish. 0.3931. This is how I spend my time. It's like I don't have a hobby. I didn't go to band practice tonight because of this, just so you know. I skipped band practice so that I could make this video so I could prepare for this class. I haven't graded your exams yet. It's a good chance that's not going to happen until this weekend. I know. How's that for delayed gratification or lack of it? Okay, so we're going to have, okay, so that's right there. We actually finished this one here, estimate that part. So now we got to get the torque. All right, so the torque that's going to be possible from this. Now they decide to use this equation right here. Ooh, they're liars. Liar and liars. Where'd you go, lying liars? All right, so their equation that they're using, that they say to use for this right here, is that very familiar, quite familiar, 63,025, but we're going to have the nominal power, which we were told was 15 horsepower. But we also were told there's a service factor, they told us, of 1.25, and they told us a safety factor of 1.1, and they're going to divide by the RPM right there. So we're like overdoing it right here. So 63,025. I'll write the thing out. Power, nom, KS, ND, all divided by N. Did I get that right? Sure. So 63,025, 15, 1.25, 1.1, and 1750. And we're going to get a torque of 742.8 inch-pounds. All right, so that was one of the things that we needed to get up above. Now, for step 4, we want to try to figure out what this delta is right here. So it's going to be this F1A minus F2, right? So this is the max, remember, max allowable belt tension going on right there. And that's going to be equal to 2 times T over the diameter right there, right? So it's going to be 2 times our 742.8 divided by 6, which is the pinion, the smaller pulley diameter right here. And from that, we get 247.6. And this should be pounds. Right, and by the way, that was step 4 right here, right? So we've got this right here. That's what we just did. Now we're going to go from here. So we're going to need tables 17.2, 17.4, and equation 12, 17.12. So let's explore those. For 17.2. 17.2. Where'd you use 17.2? Okay. So, so some of the things that we had in there was the allowable tension per unit width, right? That was the allowable tension per unit width. That's what they're referring to right here, I believe, for this. Yes, I think so. And they're also going to need a pulley correction factor for flat belts, right? So we're going to get into part of this, and we used A3, and our pulley diameter was 6. So we're going to use a 0.7 for our CP, the pulley correction factor, and the equation that we're going to use with right here, I believe, is this guy right here. All right, so we're going to use that equation to establish the allowable largest tension. Right here. So this is going to be our step 5, and we have our equation 1712 B times FA, CP, and CV. And we did find, okay, so CV, that is something that we could have looked up. Let's see. I want to double check. We found that somewhere. That is the velocity correction factor. And you could either look that up from this figure right here, right? The velocity correction factor. We got a little belt velocity and all these little things. But if you read carefully right here, for polyamide and whatever belts, CV equals 1. So the devil's in the details, and he likes them. 0.13, somewhere in there. Yep. 0.1. No, 6. It's B. Yeah, this is 6. This is the crazy width of the thing. I was thinking thickness, 6. We looked this up as 100. We looked this up as 0.7, and we just read that it was equal to 1. So we get for this 420 pounds, right? For step 6. Step 6 says that we're going to we're going to use this result right here to find out what F2 is going to be, right? That makes sense. So we just find that F2 is going to be equal to F1A minus the quantity F1A minus F2, right? Duh. That just means that we just take the thing we just found, 420. It's 420 somewhere. And I didn't just say that out loud. I don't even know what that means. 172.4 pounds. And, okay, so now we're at the step 7. Right, so we found F2, and by the way, we were doing some of the things we were supposed to do. We were supposed to find F1, F2, Fi, and now so Fi, we find that from equation I, by which they mean this guy right in here. And I haven't even tried to figure out what that means yet. It's probably from this guy right here, depending on the slack side or the other side of this thing. But that's what that's based on. So let's just write the thing out here. Where we're going to say Fi is equal to F1 plus F2 divided by 2 minus Fc. So we know F1, we just found that, right? That was 420. And then we add 172.4 divided by 2. And then we subtract out centrifugal of 25.62. We got that back up in there. And so what we're left with is 270.6 pounds. So now what we want to try to figure out is we want to do that thing where we want to confirm the coefficient of friction right there, right? So we want to check the developed friction by way of these things right here. And we didn't need that Fi for anything. So I guess that just was telling us if we had like a recommended pre-tensioning thing. By the way, I should mention how you can pre-tension things. There's several different ways. A lot of times it'll be like a mechanical adjustment that you can make on a thing. Sometimes there's a pre-tensioning little bar that comes onto the thing. That type of stuff. It's kind of interesting, maybe. Okay, so remember, that's supposed to be in radians. Don't forget. Always remember, never forget. F1 minus Fc divided by F2 minus Fc, and be sure that you just keep in mind that's like the fundamental friction relationship that is existing right here. It's actually, we can think of it as our model, right? We've modeled how the friction is distributed and made a math model of the thing, and that's been shown to work because we can't really measure that, not directly. We can measure the effect that it has of the thing. Oh, I'm sure somebody can measure it. 0.3276, and because this is less than this, I wrote since this right here is less than our 0.8, it won't slip. Of course, like I mentioned, that 0.8, who knows how good that 0.8 is going to be, right? But must be a pretty good guess. 9, it does a weird thing in the book. It doesn't actually, they got really lazy at the end, and I would too, because it's like 10 o'clock at night. I should be home. I should be driving home. It takes me an hour to get home. It's going to be 11 o'clock. So I'm not going to record the other videos tonight. I'm too tired. Just can't do it. It's not safe. But anyway, they didn't bother doing this right here. So this is what I want to do. Get what this power is going to be. This is the max allowable power based on F1 minus F2 times V divided by 33,000. Right. So I'm using this equation J, if you will, right there, to get H, even if you won't. So in this, I use my 420, and I subtract out my 172.4, and here's my velocity in feet per minute, and I divide out by 33,000, and I end up with 20.63 horsepower. So that's the maximum it can do. Right, the maximum power that it can do, because that's what we found from the geometry and the speed and everything going on. This is the maximum amount of tension that we can have. I think it's also the limiting thing based on that 100. Right, we were using this 100 right up in here. So the whole combined effect of the thing is that we've established what we can do for this for this arrangement. And so they write a safety factor here, and it's kind of a weird safety factor, but I guess it's from this right here. So we take that divided by the nominal and that KS, and then this just seems kind of weird to me, but I guess it's just a confirmation. I don't know if it's really necessary. It seems kind of weird to me. S. I'll turn that to an S. It almost wasn't an S. 20.63 divided by our 15 was the nominal, divided by our 1.25, which was given, and we get 1.1. But some of the value, I think, in this is trying to see the consequences of the friction. How to size the thing. That's my rationale for it. I think the cable thing will be better, but that's all for now. I'm going home. 28-minute video no one will ever watch.